In this module, I cover age structure estimation using what we refer to as a captive cohort method. The concept is based on a paper published in the journal Aging Cell in 2004 by Hans Mueller, Jane-Ling Wang, myself, and several other colleagues. My objective here is to outline the qualitative concept first using a simple graphic. Then, using a numerical model, I will illustrate the analytical concept. The details of the empirical and numerical methods can be found in this paper, as well as in our book. The captive cohort method is a technique that my colleagues and I developed that assumes the age structure of a wild population can be inferred from the death distribution of a randomly sampled group of individuals of unknown age, that is to say, the captive cohort. The qualitative concepts are shown here, where on the left set of graphs is the population age distribution, and the right set is the post-capture age of the death distribution. The top graph illustrates the age structure of a young population in which the death distribution of the population sampled as a captive cohort is skewed to later captive ages because they are mostly young individuals that have much life remaining. However, the bottom graphs illustrate the age distribution and subsequent death distribution of an older population in which the post-capture death distribution is skewed to the left because they are older and more frail and therefore have a higher death rate. The method is based on three cohorts. The first is the captive cohort, that is, the sample from the wild that is currently observed. The second is a reference cohort from which survival rates are derived previously in the laboratory. The third represents the wild cohorts as the population age groups that are to be determined, that is, the unknown age distribution. This shows the recursive model of simultaneous equations that is used for estimating age structure, where nx star denotes the number at captive age x. NW10 and NW15 denote the unknown number of individuals at ages 10 and 15 from the wild in the captive cohort. And Lx plus 1 over Lx gives the known reference survival from ages x to x plus 1. The first equation in the set of simultaneous equations is the number at captive age 0 that are ages 10 and 15 in our 2 age class example. The second equation in this set involves the number of individuals in this captive cohort that survived the first day, which equals the product of the number from the wild age 10 and survivorship from 10 to 11, plus the product of the number age 15 and the survivorship from 15 to 16. This next equation in this set is the number that survived to captive age 2, which equals the number from the wild age 10 times the 2-day survivorship, plus the number age 15 in the captive cohort times this cohort's 2-day survival. This same math applies to survival to subsequent captive ages. Now let's introduce actual numbers. Note that the field collected number in the captive cohort was 1,000. This constitutes the captive life table radix. Post-capture survival for subsequent days was 900, 775, 636, 495, and 364. We insert the appropriate survival probabilities for subsequent post-capture times. The objective is to solve numerically for the number at age 10 and the number at age 15, which is to say solve for the number in each of the 2 age classes in our original sample of 1,000 wild individuals. Thus, we are seeking the answer to the question, how many of unknown age in our sample were 10 days old and how many were 15 days old, i.e., what is the age structure? Note that in an actual sample, we are asking the question of the entire age distribution, not just 2 ages as in this hypothetical example. Using numerical methods to solve for the number of wild at age 10 and the number of wild at age 15 in our original sample in this set of simultaneous equations yields a solution of 800 10-day-olds and 200 15-day-olds. A summary of the model results is contained in this table. In this first column, we have captive age X star. Then for these next columns, we have flies of unknown age in a mixed age population sample. In these first 4 columns, we have the metrics for the captured 10-day-old flies, including chronological age, number, probability of surviving x to x plus 1, and dx, or the number dying in the interval. Likewise, in the next 4 columns, we have the metrics for the captured 15-day-old flies, including chronological age, number at age x, probability of surviving x to x plus 1, and the number dying in the interval. And in the last column, we have the captive cohort, including the total number, which equals the 800 10-day-old flies and the 200 15-day-old flies, totaling 1,000 in the radix. And the number of dying in the cohort, of which is 40 and 60, equal the 100 from captive age x star to captive age x star plus 1. This illustrates the fundamental concept of the numerical solution to finding the age distribution of a wild population. This method is based on what is referred to as the memoryless assumption, where the mortality risk of wild-caught individuals maintained in the laboratory will be identical to the mortality risk of individuals reared in the laboratory of identical ages. Although this assumption is likely violated to varying degrees, the captive cohort method provides a unique and qualitatively different approach to estimating age structure than previous methods, such as those involving chemical analysis or wear and tear estimations, each of which is limited by their own set of often violated assumptions. This ends this last module of Chapter 9.